what is going on with quantum computing right now. If you've glanced at any tech news lately, you've probably seen the wild claims, right? That quantum computers are either going to solve literally all of humanity's problems tomorrow, or they're going to completely break global encryption by next Tuesday. Well, the reality is incredibly fascinating, but it's a bit more complicated than those flashy headlines suggest. Today, we're going to dig into where the tech actually stands, the massive hurdles it still has to clear, and the absolutely mind-blowing potential it holds if we can get it right. First off, we need to talk about the sheer scale of the investment here. $56.7 billion. That is the total global public funding committed for quantum research up to 2026. I mean, this isn't just some niche science experiment happening in a university basement anymore. It's a full-blown global race. Public funding jumped by over $12 billion in just the last year alone. And right alongside that public money, we've got a rapidly accelerating $1.4 billion commercial quantum computing market, plus venture capital surging to nearly $5 billion. The world's biggest economies, North America, Europe, and a really aggressive Asia-Pacific region, are pouring absolute fortunes into this space. So with all that cash flying around from tech giants and governments, we really need to ask why? Why is this technology suddenly scaling right now to the point that nations are basically treating it like a new space race? To really grasp that, we have to look way past the standard silicon chips sitting in our laptops and phones right now. See, we are no longer just theorizing about physical qubits, we're actively building them. We're doing wild stuff like trapping individual electrons and hydrogen atoms to manipulate their spin, or leveraging photon polarization. By forcing these microscopic systems into a state of superposition and harnessing entanglement, where qubits instantly influence each other even across distances, we are cracking open an entirely new type of computational state space. Think about your standard classical bits, kind of like simple light switches. They're either off or on, a 0 or a 1. But qubits? Qubits allow us to sample from a vast, probabilistic distribution of both states simultaneously. When you run a quantum algorithm, you aren't just processing linearly faster. You're actually mapping complex multidimensional problems directly onto the quantum states themselves. It essentially lets these machines handle specific calculations at a scale that classical silicon literally couldn't crack in a million years.